Record on this computer. Okay, welcome back to Organic Chemistry 2341. Here it is on a Wednesday afternoon. So we're going to continue on with our discussion about E1, E2. And I want to show you in this reaction diagram the fact that they are in competition and how we can influence the product ratio. So in the case of this reaction diagram, we have the same intermediate. We have that carbocation intermediate, and that carbocation intermediate that has to go through that second step. We have two possibilities. We have a small activation energy for the SN1, the substitution product, and we have a larger activation energy for the E1 product. Okay, so that means at a lower temperature, there's not going to be very few molecules that will go over that higher energy barrier, and we'll predominantly get the SN1 product. However, by increasing the temperature, we'll have more molecules that can overcome this higher energy barrier, and we can increase the amount of our elimination product. So going from at lower temperatures an 80-20 mixture, we can probably get that to a 60-40 mixture. But the SN1 product will always dominate because it has the lower activation energy. And it's also the more thermodynamically stable product. Okay, so that gives us something about that as well. Notice because we have that double bond is higher in stored energy, and therefore it is also not the thermodynamic product, and it's not the kinetic product either. So it's this product of a different mechanism using a different activation energy. Okay, so what does this mean? Well, that means that the higher temperatures will increase the portion of the elimination product because we have more molecules that can overcome that second higher energy barrier. Okay, so the SN1 reaction with the alkyl halides will always produce a mixture, but we can, by raising that temperature, increase the amount of the elimination product. We can never get rid of that SN1 product unless you have a super big and bulky base, but we don't have that. Okay, even then it has a little bit. Okay, so what does that mean? Well, that means that if we have it at lower temperature with a weak base, so it's less likely to pull that proton off real quickly, and a tertiary carbon in a polar solvent, we're going to have the SN1 is favored. Okay, so again, SN1 is going to be dominant in all of these. However, we can increase the amount of the elimination product with a higher temperature, a stronger base. Again, we're still using a tertiary carbon, so we can get that carbocation and a polar protic solvent. So notice in all of the unimolecular systems, polar protic solvents help stabilize that carbocation. That carbocation is the first step in both of these mechanisms. And the only thing we're doing next is if we have a weak base versus a strong base, we can get to an elimination product. Think about it as the stronger base is going to remove the acid instead of just displace the halogen to give us our elimination products. Okay, so we typically don't use the SN1 reaction as much. We really want to use it for the E1 reaction because number one, we get a mixture of stereocenters if we're doing an SN1 reaction, and there's always a little bit of the E1 in the product anyway, so we don't have significantly good yields. Okay, so we'll talk about how we can change that mechanism, force it to go with an E2 mechanism that we'll talk about in the next chapter. The E2 mechanism is actually much more useful synthetically because it's more precise on how it does its elimination. Okay, so we said before that the alkenes have stability based on the number of substituents you have, right? So if you have one substituent, that's not as stable as two substituents, and that's not as stable as three substituents or four substituents on our alkene, okay? So there's a rule we use to tell us how to get to that more substituted alkene, okay? What we call that, it's called the Zaitsev Rule. And what Zaitsev Rule says is that if you have a choice between hydrogens, the beta hydrogens that are next to your carbocation, you're going to remove the hydrogen from the one that is more substituted. Okay, so let's take a look at that and talk about that in a minute. Okay, so in this case here, we have our alpha carbon. This is where our carbocation center is going to be. And we have beta carbons on these two methyl groups, and they're equivalent because it's a methyl group. It has 3 hydrogens, and so those are basically the same as far as acidity and as far as the product that they would give. But over here on this beta carbon, we have another carbon on it. Okay, so what does that mean for us? Well, that means that we have a choice between these 6 beta hydrogens and these 2 beta hydrogens to give us our product ratio. But remember, we want to have the most stable alkene possible. So we want to choose the alkene, we want to choose the beta hydrogen that's going to give us the most substitute. And in all the cases, you're going to find that it's going to be the beta hydrogen that is on the more substituted carbon. Okay, so this is going to be a primary carbon because it only has 1 carbon attached to it. This is, let me use a green here. This is a secondary carbon. Okay, so if you have a choice between pulling a hydrogen off a primary carbon or a secondary carbon, it will always pull it off the secondary carbon. Why? Because when it pulls it off the secondary carbon, it's going to give the more substituted alkene. Okay, so let's do that. And so let's run through this. Once we form our carbocation, we have SN1 happening, right? So what would the SN1 look like? Well, it's going to react with the solvent here, in this case, methanol. And that SN1 is going to give us this product here after we deproton here. It's going to give us an ether, okay? And apparently we're doing this at a fairly low temperature because we have the SN1 product dominant. It's very high, 60%, okay? But what if we pulled off a hydrogen from one of these primary carbons right here, okay? So if we pulled off a hydrogen from the primary carbon, we're going to end up with an alkene, but it's going to be an alkene that has 2 substitutions on it when we redraw it right here. And we do get this product, but that's not the thermodynamically more stable product. So let's try pulling the hydrogen off the other side. So we're going to pull it off the secondary carbocation, secondary carbon here instead. When we do that, we actually end up getting a more substituted alkene. Our product has 3 substitution here. And so this is the greater thermodynamic product between the 2 alkenes. And of course, this is still the better thermodynamic product because it does not have the double bond. So it follows that rule as well. So look at the product ratio here. This is smaller than that. It's about 1/4 of what the more substituted alkene gives us. So net result, Zaitsev's rule is if you have a choice between 2 carbons, the carbon with the higher order is going to be the one you should pull it off to give the more stable product. So if you have a choice between a secondary and a tertiary, it's going to try to pull it off that tertiary carbon. If you have a choice between a primary and a secondary, it's going to pull it off that secondary carbon. If you have 3 primary carbons, it doesn't matter. It's going to be a symmetrical molecule anyway. Okay? Questions on Zaitsev's rule? Okay, so again, now when we look at these reactions, we're looking at a little bit of the thermodynamics, a little bit of the kinetics, and a little bit of the mechanism. And you can start talking yourself through the thing saying, well, what's the most stable product? That's probably going to be the highest part, the highest yield in the product. Okay, so let's look at that energy diagram as far as we go through the eliminations and the substitutions right here. So in the case of this, we have a choice of this compound right here. And this would be these are going to be our blue beta hydrogens, and this was our green beta hydrogen. What is over here? Okay. And again, the substitution product has the lower activation energy, but we're not going to draw that on here. That's why this is going to be the major product. But let's just look at the elimination reactions, okay? When we look at the elimination reactions and we're pulling the hydrogen off of the secondary carbon, when we're pulling that hydrogen off the secondary carbon, it actually has a lower activation energy and a greater exotherm. It's the more thermodynamically stable product. When we have the other reaction happening, where we're pulling it off this beta, the blue beta one right here, that's actually a higher energy transition state because we're putting our partially positive charge over here. And when we have these electrons kick in here, it gives us the less substituted, less thermodynamically favored product. So even the transition state is higher in energy compared with the transition state of the secondary hydrogen elimination. Okay. So let's use this to our advantage and change the mechanism slightly. What we're going to do is, instead of using the halogen as the leaving group, we're going to make water a leaving group. And this is called dehydration of alcohols, but it undergoes some of the same mechanistic steps we saw in that E1 reaction. Okay, we just have to change what our leaving group is and what our base is. Okay, so let's talk about that. So if we look at this reaction here, and we have two types of beta hydrogens. We have the primary beta hydrogen, and a secondary beta hydrogen here. So we can predict that we would get the removal at this secondary beta hydrogen to give our major product of the alcohol elimination, the alkene. Okay. Now notice that there is no substitution product in this. There's no SN1 product in this because we don't have any nucleophiles. All we have is a very weak nucleophile and a base. So when we do the dehydration of alcohols, we don't have to worry about that SN1. It only goes through the E1 elimination, and it only gives alkenes in their product ratio. So this is much more synthetically useful to produce an alkene than to use an alkyl halide. Okay, so let's change that up again and look at this. We have a primary, let me do that in blue then. We have a primary beta hydrogen. We have a secondary beta hydrogen, but we'll end up with a stereochemistry problem here, okay? If we have free rotation of this sigma bond before we do the elimination, we can end up with our cis isomer, okay? If we rotate that down so that the bond is sticking down here, we're gonna form our cis alkene, okay? Now, if we don't do that, we have free rotation rotated back and it's still there. We are still going to eliminate our beta hydrogen on our secondary site much more readily. When we do that, that gives us the trans alkene, okay? Now, statistically, we still have 3 hydrogens here that we can pull off, and some of the, even though it's a higher energy transition state, some of the molecules will go over that, and that will give us our terminal alkene right here, okay? So notice of these, the major product is the most thermodynamically stable. The second major product is the second most thermodynamically stable. And the last product is the least thermodynamically stable, okay? So whenever you attack these E1 problems, you wanna make sure you're trying to get the higher order hydrogen eliminated first, and that determines your major product. All right, questions on that? So yeah, dehydrating alcohols is much more synthetically useful. Okay, so let's go the mechanism step by step. I want to show you what becomes the base and what becomes the leaving group here. OH by itself is a horrible leaving group. OH negative is a horrible leaving group because it's a really strong base and it's a really good nucleophile, right? So we have to trick it. And so the first thing we can do to trick it is to add a proton to that alcohol to give it the oxonium ion. Our oxonium ion then is ready to leave as neutral water. Okay, so the first thing we do is we have our acid. Our acid donates a hydrogen to the oxygen, giving us our oxonium ion, okay, plus this right here. This is our hydrogen sulfate, right? I mean, yeah. it is now our base. Okay, we lost a proton, it is now our conjugate base. It's going to be the base in our system. Okay, now let's go ahead and see what happens. All right, great. We form our tertiary carbocation here, and we had water leave as our leaving group as a neutral. Now it is also a weak base. Okay, so then the next step has to do with what happens next. A base has to come in and remove one of the beta hydrogens, okay? And here we have a choice between our beta hydrogen on our primary carbon here, or a beta hydrogen on our secondary carbon here. If we eliminate that beta hydrogen on that secondary carbon, see how these, well, let's see, this, trying to do purple. See how these arrows are purple here? These purple arrows are going to undergo this type of proton transfer. So the purple arrows are removing the hydrogen from that primary thing. When it does that, it gives us our least substituted alkene. However, if we follow the gold arrows here and it removes the secondary beta hydrogen, we end up forming the more substituted alkene, the more thermodynamically stable alkene, and therefore the major product. Okay, so does that make sense that we're using our base? And because it's a weak base, it can wait around and wait for the more thermodynamically stable hydrogen. Okay, now statistically, you'd think, oh gosh, I have 6 of these hydrogens over here, and I only have 1 of these hydrogens over here. Oh, 2 of these hydrogens over here, sorry. So it's going to take the one at the other side. It's like, no, the thermodynamics are more important in this, and we will get the more stable product when we get it. Okay? All right, so let's look at that reaction diagram now. It seems to have a whole bunch of steps, but we can explain every single step in the reaction diagram. Okay, the first thing that's going to happen is we are going to have our starting materials, and it's going to transfer a proton from the acid to the alcohol, giving us our first intermediate, our oxonium cation. Okay, so then we have to go through another energy barrier to have that water leave as neutral water, giving us our intermediate carbocation here. And now we have 2 paths. Okay, we have the lower energy path of removing the secondary hydrogen and the higher energy path of removing the primary hydrogen. Okay, so when we do that, when we remove that primary hydrogen, it cascades down into our less stable product. But in this case here, we actually are transitioned down to our protonated species. Oh no, this is right here. It's actually undergoing a carbocation rearrangement to a more stable carbocation. In this case, we're going from a secondary carbocation, let me blow that up, to a tertiary carbocation. So if we had enough energy for it to actually eliminate, we'd create 1 product. If it sat around and decided, hey, I want to be a tertiary carbocation, it's going to transfer to getting a more stable carbocation. Notice how this is more stable. And then we do that proton transfer to that more stable carbocation. When we do that, we'll end up with our 2 possible products, eliminating from our primary. This is eliminating from our primary, and this is the one eliminating from our secondary. Notice the one eliminating from our secondary hydrogen here gives us our more substituted product. Okay. So the other thing to think about here is like, okay, why are there 3 products? Well, we have to always remember, whenever you form a secondary carbocation, it's possible to do a 1,2 hydrogen shift or a 1,2 methyl shift. Okay, so in this case, we are going from the carbocation on a secondary carbon. In the case of our first intermediate, it's transitioning to a tertiary carbocation, and during that time, it's getting to be more stable. but now it still has the choice between our secondary hydrogen or our primary hydrogens, and that gives rise to the two products here. Okay? Are we starting to get this, the E1 mechanism, and starting to see how we could get different products just by following the electrons around? Okay? Any questions on this? Okay, all right. So let's see how it affects the stereochemistry. And when we talk about stereochemistry with alkenes, we're talking about cis, trans, or E and Z, okay? So let's go ahead and say we have our beta hydrogens here. And hey, great, they're equal. It doesn't matter, right? Because that's a secondary here, that's a secondary here, okay? Well, we do have stereochemistry here because remember, when we have sigma bonds, we have free rotation around these sigma bonds. And so instead of having our methyl group, terminal methyl group on this one side over here, oops, sorry, over here, instead of this, it's going to swing around and be down here. If it's in that part of the rotation, when you form your carbocation, remember your carbocation is trigonal planar, it will lock it in that position and then it'll make the alkene. So we have our product ratio is our cis as our minor product, because it's going to spend less of that time in that close in cis state, and our trans will be our major product. Okay. Also, the trans is more thermodynamically stable than the cis, and so you will always get your more thermodynamically stable product, in this case, our trans product. Okay. So, but notice that it doesn't matter which of the beta hydrogens you took off to make this product. It could be on either one of these, and it would make the exact same system right here. So either way you did it, you're going to form your carbocation on that center stage, and then you can remove one or the other to make that product. It's just where your methyl group has rotated around, and then it pulled off the secondary hydrogen. Okay, let's see. And that is the end of chapter 7.1. Okay, questions on E1, because we're going to move into E2 next. All right, unimolecular, always form a carbocation. Whenever you form a carbocation, watch out for it, rearrangement. Okay, let's go to this one. No, that's not right. This one. E2, okay. So E2 reaction, as the name suggests, is going to be a bimolecular reaction. Therefore, the base itself is going to be present in the transition state, okay? So if the nucleophile is a strong base, you can have, instead of the substitution reaction, you can act as more of a base and less of a nucleophile and cause an elimination reaction, okay? But depending on how strong your base is, you can actually have competing reactions or destroy it one way or the other, okay? So let's start out with something simple like methanol in alkoxide right here. I mean, this is the sodium salt of methanol, and it's in methanol. So we have a polar protic solvent, we have a strong base, and we have a primary alkyl halide, okay? So primary alkyl halides almost never form carbocations, so it's not going to do that. But what we're going to see, our major product is going to be our substitution product, because it's small, it's a good nucleophile, and it's in a protic solvent. It gives us predominantly our substitution product. But because it's such a strong base, we do see the formation of some of the elimination product. Okay, so let's think about how we can get more of the alkene. We really want the alkene. We're trying to make alkenes in this chapter. So how can we trick that, okay? Well, why don't we move to a group that would more likely form a carbocation? Let's go to a secondary alkyl halide, okay? When we go to the secondary alkyl halide, now look at this. We have two methyl groups here that's starting to get sterically hindered, right? Steric hindrance decreases the chance of an SN2 reaction because those methyls are in the way. And look what the product ratio did. We've now flip-flopped. We have a minor product is the substitution product, and the major product is the elimination product. Okay? That is to do with the sterics of the situation. We have no steric demand here and mostly substitution. We have the second highest steric demand. The only way to go higher is doing tertiary. We start getting predominantly the elimination product right here. So then if we went to a tertiary, our substitution should drop to 0, and we should get 100% of our elimination product because of sterics, and that's what we see. Notice these are all approximately the same nucleophilic strength, okay? It's the methanol and ethanol have about the same acidity, therefore their base strengths are about the same as well, okay? So the only thing that changed here was our steric demand on our substrate. Okay. Questions on that? Okay, so like I said before, it's a bimolecular reaction. The base has to be starting to tug on that beta hydrogen before the leaving group leaves. Okay, so we have to have a slightly different coordinate diagram, but the key here is that because it's bimolecular, the concentration of the base and the concentration of the substrate are both important. If you double one, it doubles the rate. If you double both, it quadruples the rate, just like in the ESN2 reactions, okay? Now, it also is a concerted reaction, okay? So our reaction diagram should look a lot like an SN2 reaction diagram, except that we're not going to give off as much heat because we're forming an alkene, which has more stored potential energy. Okay, so that means we have to have a different transition state. In our SN2, our transition state was we have our groups here and they are going flat, and we have our nucleophile coming in 180 degrees from our leaving group, okay? We don't do that in the E2 reaction because the base is actually pulling on a beta hydrogen, okay? So that means our intermediate here is actually looks more like this, okay? So the first thing we have is our alkoxide with our anion comes here. It is a base, and therefore it's going to use those electrons to pull off a proton, okay? But it has to be the beta proton. If it pulled off this proton, there's no leaving group, okay? So it's not going to pull off the proton on the carbon with the halogen on it, okay? So it has to pull it off beta to that halogen. And when it does that, the electrons, as it's breaking this bond right here, those electrons are going to kick in here, okay? When those electrons kicks in here, that's going to give a total of 10 electrons around carbon, so we can't have that. And so what's going to happen is the bromine is going to take these electrons away when it leaves, okay? So we have electrons from the base pulling a hydrogen away. We have the electrons from the hydrogen going to form our double bond, and the electrons between our carbon and our halogen leaving with the halogen. And it happens all in one step, okay? And then that way we end up with our products. Our products are a neutral alkene, a neutral base, and a leaving group as an ion. Okay, so that means if we have everything happening all at once, we have one hump in our energy diagram, okay? So, and the height of this right here will depend on what type of hydrogen we have here. If you have the chance between a primary halogen, a primary and a secondary, it's not as easy with E1 as it was with E1, because now we have to worry about sterics. How can my base come in and pull off other hydrogens? Okay, so let's look at that. Oops, wait a minute. All right, so questions about that concerted step. Notice 3 pairs of electrons are moving all at the same time, creating a new bond, creating a double bond, and breaking a bond to form an ion. Okay. All right. So Zaitsev rule also applies here, okay? We're gonna try to eliminate the one to give us the highest, the most stable alkene until we start seeing sterics give us trouble. So in this case here, we have a beta hydrogen that is a secondary beta hydrogen. Here we have beta hydrogens that are primary beta hydrogens. So if we had it go to the primary beta hydrogen, we would end up with our terminal alkene at about 20%. Okay. But again, this one right here, we only have a methyl group here. It's not being crowded out too much. It can still act as a nice strong base. And that gives us our major product, the internal alkene. Now, notice that could be cis or trans. We're just going to say it's a mixture of the two is that major product. So the mixture of the cis and trans is here, and then that terminal alkene is here. Okay, so Zaitsev rule does apply, but we can increase our chances of that by changing the nature of our base. Okay, so should I? Yeah, I probably should. Okay, so one of the reasons that the Zaitsev rule works so well is because as you're starting to tug on that hydrogen, you're starting to form a partially positive side of our system, and it's going to be the more substituted one that's going to be partially positive. And so because this side is partially positive because the hydrogen is being pulled away, it will try to have as many things contributing to it as possible. Okay, all alkyl groups are donating groups. They can contribute to that pi bond. So having that hyperconjugation in your final product stabilizes your final product, okay, which leads to a higher concentration of your more substituted alkene. Okay, so because it's pulling it off at a specific location to give a specific product, we tend to call this a Regio selective process, meaning that it prefers one conformation over another. And again, it follows Zaitsev rule. It says that you're going to remove the hydrogen from the more substituted carbon. When you remove the hydrogen from the more substituted carbon, you get the more substituted alkene. Okay, question on that or not? All right, so and the whole reason comes down to that activation energy of the two different groups, okay? So let's look at this one first, the smaller one here. When we start taking our alkyl halide here is a tertiary alkyl halide, and we have a choice of the hydrogens over here, which are primary, or the hydrogen right here, which is a secondary, okay? Turns out when we try to remove the hydrogen from that secondary carbon, it's easier to remove because it has a lower activation energy, okay? So if we controlled our temperature very carefully and only gave enough energy so a majority of our species only had barely enough energy to overcome that first energy barrier, we would get predominantly our tri-substituted product because it's the lower activation energy because we're using a secondary hydrogen instead of a primary hydrogen. Let's say we went the other way and actually decided to take it off one of the primary hydrogens here. That's a higher activation energy, okay? Because the product it's forming is not as stable. Remember the Hammett principle, what's looking more like the product and more like the reactant, right? So we're looking at something that looks more like product and it's going to be lower in energy than the one that looks more like starting material, and therefore it is a higher activation energy. And we end up with this, removing the primary, we only get our di-substituted product. Okay, so questions on that. So notice they have a different amount of exotherm. We took more energy to make it, and it made the thermodynamically less stable product. Okay, and if we had really high energy, we'd still have enough of this, but we'd have a lot of this. So it turns out the tri-substituted alkene is both the kinetic and the thermodynamic product. So it's going to be our major product. All right, let's see, 7, all right. So let's think about what's happening to those electrons in those states. Let's convince ourselves that pulling off that secondary hydrogen is better then pulling off that primary hydrogen. Okay. One of the other things we have to think about is that this is a concerted reaction, okay? Meaning that all the electrons are moving at one time, which means we have to have things arranged just right so that these electrons can move in here, these electrons can move out here, where we're not moving or translating any of the other substituents of the products, okay? So what we're gonna look for is having the hydrogen being pulled off anti to the halogen, okay? Now let's take a look at that and remember our Fischer projections when we do this, okay? So if we're looking at this, we have our two sp3 hybridized carbons, and our transition state is where the base is pulling off this hydrogen here, creating a new sigma bond. This sigma bond is turning into our pi bond, and this sigma bond is leaving with our leaving group to give us our pi bonds here, okay? Now let's redraw this compound as a Fischer diagram, okay? So the way we would remember how we do that, we're gonna do the rear here has a methyl group on it and a hydrogen on it and a bromine on it. And then the front has a methyl group on it, CH3, H, and H here, okay? So go back and remember how to convert this to that. Now, two things to note here, okay? Why is this the preferred configuration? Well, the methyl groups are opposite each other. The methyl groups are anti to each other, so that's going to be a favorable way for it to happen. But the other thing we have for us going now is that the hydrogen is now anti to our leaving group, okay? This structure of having the hydrogen anti to our leaving group is going to make it easier to remove that hydrogen because the electrons are just going to flip in and break a bond, make a bond, and break a bond all at the same time. Okay? So it's much easier to see on that Fischer projection than in here, but the idea is that you want them all in the same plane, and we want them opposite each other so that they can move the electrons around more easily. All right. So when we do that, we're looking at going from an sp3 hybridized carbon to an sp2 hybridized carbon in the process. And so what's happening in that condition is as the hydrogen gets pulled away, the sp orbital that was bound to it breaks apart and turns into its s orbital, and its the s orbital is then shared with the other sp3 hybridized orbitals to turn them into sp2 orbitals, and then the p orbital is pulled out of that such that the p orbital is going to align with the p orbital on the next carbon over. So, but what happens to the other side? Well, as the leading group leaves, right here, the other lobe of that p orbital, as it's breaking, becomes the new p orbital. Notice they're tilted about the same direction. That allows them to get fully perpendicular when it converts completely to trigonal planar, and they're overlapping perfectly to give us our double bond. Okay. Remember, we have to have perfect alignment of the both halves of the p orbital to get a really good double bond, pi bond, right? I think there's an animation in the book that might actually show this. So, okay. And no, I don't want to do that slide. All right, so let's talk about stereochemistry. Okay, so in the stereochemistry, depending on how you start with the material in its form, it's going to favor one product versus another, and it's also going to favor one conformation is going to react well, and the other conformations won't react well. Okay, so let's look at the first one. Okay, let's look at it where we have our methyl groups opposite each other in that anti-state. And if we look at where those new orbitals are going to be formed, where those new pi orbitals are going to be formed, they're going to be formed in this plane because of the hydrogen was bonded sticking up, right? And that new p orbital is going to be aligned with that where the hydrogen is. And if we look at the back here, the back was also an sp hybridized orbital, but it's going to break and become a p orbital. And notice that because that sp orbital was sticking down, that the bond was sticking down, it's going to align there. So our hydrogen and our bromine are lined up. This is the best configuration because as we're breaking the hydrogen off and as the bromine are going, those two new p orbitals are perfectly aligned and it makes a great pi bond. Okay. What if you have it a different way? Okay. Let's instead rotate this around by 180 degrees. So we've rotated this 180 degrees so that now the hydrogen and the bromine are overlapping. Okay. So if the hydrogen and bromine are overlapping, when we try to form this right here, this is the part of the P that's starting to form, and this is the other part of the P that's starting to form. It's actually kind of almost the different lobes are in opposite directions of where they should be. And because it's in opposite directions, it doesn't actually have a favorable. Notice one is going to be pointing a little away from the other one. They're not pointing all in the same direction, and so it's less stable. And so the configuration to create this double bond when it's in this position doesn't happen very often. So, but we do have that free rotation. So if it rotates around such that we have them in this staggered formation now, again, we don't have good orbital overlap when we try to form those P's. Because we don't have that good orbital overlap, it doesn't actually react in that condition. So we can't actually get that configuration to react. Okay, so whenever you want to look at this, always have your hydrogen and your bromine 180 degrees apart from each other, staggered. And if you have to draw it as a Fischer projection to make sure they are, that's going to help determine your stereochemistry of your final product. Notice methyl group on this side, methyl group on this side, it's going to give us our trans isomer. Okay, so you can always back through the Fischer projection to get to your isomer ratio. Okay, so questions on that? I know this is a little hard. We got to keep all these things in our heads at the same time. Okay, so let's make things easier by turning them into a ring. Okay, so when we turn them into the ring, we have, hydrogens we can eliminate, but we can actually know which hydrogens we can eliminate and which hydrogens we can eliminate because we're looking for that 180 degrees apart, right? So we actually have a preference of certain the axial hydrogens versus the equatorial hydrogens when we do this reaction, okay? So, but again, it doesn't matter whether it's axial or equatorial when it's sitting here, we're gonna give the same product, okay? So, but which hydrogen is gonna be eliminated? Well, again, when we're looking down a bond right here, we're gonna look down this bond between carbon 1 and carbon 2, right here. Actually, it's purple, so I'll go back to purple. This bond here is what we're looking down, so we're looking in this direction here. Oh, actually, we're looking in the other direction. We're looking up 2 first and then 1 second. And when we do this, we can see that the axial hydrogen right here is opposite that axial bromine, okay? So in this configuration, the axial hydrogen and the axial bromine are going to be the ones to leave and give us our alkene right here, and all the other hydrogens stay there. Okay. So, and note that this is on our number 3 carbon, so we're not worried about that. So we've taken our hydrogen off of our number 2 carbon, our number 1 carbon, and our bromine off our number 2 carbon to form this. Okay. Now, remember, cyclohexane rings flip back and forth, back and forth, back and forth. So what if we had in the other configuration? If we had it in with the bromine in the equatorial position? Well, let's look at what happens when we have the bromine in the equatorial position. In this case, we don't have any hydrogens that are opposite the bromine. We have a methyl group. Okay. So that means in that particular configuration where the bromine is in the equatorial position, which is where it might spend a lot of its time because it's a big group, right? It's not going to react. Okay. So because it doesn't have a hydrogen in that 180 position. So what that means is this particular isomer, even though it's going to be the more common isomer, does not undergo an E2 elimination. But when it flips back to this other side where you have your hydrogen opposite your bromine, it does undergo E2 elimination. Okay. And so you only have the one actual conformer that does the reaction. The other one is just not useful and flips back and forth until we can use it. Does that make sense about how to use that Fischer diagram to make sure your hydrogens and bromines are opposite each other? Okay. All right. So let's see what time. Oh, plenty of time. All right. Okay, so if that has to happen, if we have to have that hydrogen and that bromine or that hydrogen and a leading group opposite each other, that means we're going to favor one possible product over another possible product because of that ability to form that transition state, okay? So in this case, we might actually not necessarily follow Zaitsev rule because we cannot get into the conformation that would give us the more substituted alkene. But we know this because by drawing out our Fischer diagram, we'll know that which configuration we have our hydrogen opposite. Okay, so let's take this for example here. And in this example right here, we have a T-butyl group here, a methyl group, and our bromine here. So obviously that T-butyl group is going to want to be equatorial. Okay, so let's figure out where our bromines and methyl groups are when we see this. Okay, so let's draw this out here. Notice our T-butyl group is in its equatorial position, exactly where it should be. When it is, because our methyl group's pointed up and our bromines pointed down, that means our methyl group is axial and our bromine is axial. Okay, T-butyl group here is telling us exactly how that ring is going to be in that configuration 99% of the time. Okay, so if we look down this bond with the number 1 and the number 1 and number 6 right here, we see that our bromine is axial and we have a hydrogen that's axial. So we have a configuration that is favorable to react, okay? But it's only a secondary carbon. Zaitsev rule said we wanted to do it on the more substituted carbon. So let's look at this number 2 right here, okay? If we look at that number 2 methyl group, number 2 group as being also axial, and our bromine being also axial, we do not have a hydrogen to eliminate. We do not have a hydrogen that's 180 degrees away, meaning that that conformer is not going to do it, and we're not going to pull off this hydrogen. We can't pull off this hydrogen because it's this one over here that's next to us. It's not going to pull off the hydrogen that's there because the orbital overlap isn't there, which means we are actually going to get the non-Zaitsev rule because of locking this in place right here. Okay, so, and in this case here, even if it did, remember it's going to be this 99% of the time and this 1% of the time. In this conformer here, there is never a hydrogen opposite our bromine. And so in this conformer, there's no reaction either. In this conformer, we can only remove one hydrogen, one position, and it actually gives us only one product. Notice it's the less substituted alkene, but we're locked in place by this T-butyl group. Okay, so that's the importance of knowing that 180 degrees apart between the hydrogen and our leading group. Okay, all right, does that make a lot of sense now that we have to have that condition? Okay, so when we're picking out what our major products are, we have to think about, can I get the hydrogen and the leading group in that 180 degree position? If I can, I bet that's my most favorable product. Okay, So let's do that again with something. Oh, this is the same reaction. Yeah. So this is this is a different reaction because notice we have the different regiochemistry. We have them all up right here. In the other one, we had the bromine and the T-butyl group in the same configuration with the methyl group opposite. This is a different isomer. And we have 3 stereocenters, so it's one of 8 different possible isomers. Once we get to this isomer, we have to prove to ourselves that what product ratio we can get. So the first thing we're going to do is we're going to draw our configuration with our T-butyl group in our axial position, because that's where it's going to be 99% of the time. And we're going to see, can we get that interaction on both sides of the leaving group? So we're going to look at the interaction on this one here. When we look at that, we have the methyl group and the bromine here, and we do have a hydrogen. Notice it's this hydrogen here, opposite of bromine, and therefore it can undergo E2 elimination in that configuration. Okay, so this side is possible. So this gives us the more substituted, this gives us the Zaitsev rule here. Let's look at the other side. Okay, so we're looking at our bromine here, going over here, and we have a hydrogen here. If we draw our Fischer diagram, we're going to see that we do have the hydrogen 180 degrees. So it also can eliminate there. Okay, so it can eliminate at both, but between the two, which one is going to be more likely to eliminate? The red hydrogen or the blue hydrogen?
The blue.
So why would the blue?
Less sterically hindered.
But it forms the less thermodynamically stable alkene. So you're muted again. So I'm going to say in this particular configuration, the red one's going to be favored because we're eliminating from a tertiary hydrogen. This is a secondary hydrogen. Okay, so I think this is slightly favored because of that. Now, let's flip it to put the axial in the, to put the T-butyl group in that axial position up here. Again, 1% of the time, we'll do this. When we do that, we still get both of the hydrogens can eliminate in, oops, sorry, that's the wrong one. Both of the conformations have bromine opposite a hydrogen, so both conformations can be produced. However, because this is our secondary hydrogen, it's going to be favored. This is our, tertiary hydrogen. It'll be favored. This is our secondary hydrogen, and it'll be slightly less, but it'll still work because they both have that 180 degree apart. So if we looked at that, we would end up with a mixture of these two products right here, probably favoring the number 2 a little bit because of the idea that we're forming the more substituted alkene. Okay, but again, reaction in this state gives us the 1, reaction in this state gives us the 2, reaction in this state gives us the 1, and reaction in this state gives us the 2. So all 4 of them can react. So this probably reacts a lot faster than the other one because all 4 conformations give elimination products. Okay, questions on that? Okay, so let's do a little bit more about that stereochemistry. The trans isomer is usually produced in the greatest amount because it is the most thermodynamically stable. However, it's not regioselective, but it's stereoselective. I'm sorry, it is regioselective because we're trying to form the alkene internally, right here, as a preference, but it's also stereoselective because we're going to form the trans as our dominant stereoisomer. Okay, so even though it can react to form all 3 products, our dominant isomer is going to be the more thermodynamically stable And the more thermodynamically stable is the one that's internal and trans, or the most substituted and least steric hindered. So let's predict our transitions that we have to make our transbutene over our cis-butene. Okay. So because we have free rotation around that bond, what we're going to do is, in the case of making our transalkene, we're going to start with our methyl groups opposite each other. And notice we still have our hydrogen 180 degrees apart from our bromine here. But we're going to take off this first hydrogen here with the methyl groups in that anti-configuration. So I'm going to do this, the 1 and the 2. So we have our hydrogen up here. We have our methyl group back here. We have our hydrogen B right here. And then if we draw the back right here, we have a hydrogen here, a methyl group here, and our bromine down here. Okay, so in this configuration, our methyl groups are opposite each other, and we still have the red hydrogen is the one that's opposite the bromine. When we deprotonate that and do our concerted reaction, that will yield our trans product because our methyl groups are opposite each other. Okay. What if we rotated this just 120 degrees? We'd come up with this configuration here. Okay, so let's draw our same diagram here. We're going to do, let's see, our B hydrogen is facing up. B hydrogen is facing up. Our red hydrogen is back here. And our methyl group is over here. Then let's see what's behind here. What we have behind here. We have a hydrogen over here. We have a methyl group over here, and we have a bromine over here. So in this configuration, we have our bromine, our blue, our hydrogen is opposite our leading group, but our methyl groups are close to each other. So in this configuration, just by removing a different hydrogen, it's giving us the cis configuration. This gives us the trans configuration. And it's difficult to see without that Fischer projection, at least for me. So, but do you see why this configuration is giving the trans? Because the methyl groups are opposite each other, and this configuration is giving the cis. And we're just having a preferential removal of one hydrogen versus the other because of the stability of that conformer. Questions? Hello? Still on? Okay, good. All right. So, like I said before, the best way to do this is to look at it as a Newman projection. So you want to look for the conformer that gives you the two substituents opposite each other. And as long as there's a hydrogen available to take off that's 180 degrees from your leaving group, it will form your trans alkene. Okay. Now, if we go to our other conformer, as long as there's a hydrogen opposite our leaving group, but the two methyl groups are on the same side, it will give our cis alkene. Okay. So we're still removing the hydrogen from the same side, and we can get in the anti-position easily. All right. So let's try to think about it from an energy perspective now, okay? So what we're looking at is the two different conformers have different energies, right? Because the methyl groups take energy to spin past each other, and there's strain associated with having two methyl groups on the same side. So what that's telling us is this conformer has a starting higher energy, okay? Because those two methyl groups are giving it strain, they're pushing away from each other, and so this conformer is higher energy than having them anti to each other, having them opposite each other. So this is the lowest energy conformation we can have in that molecule. And so we have a lower starting energy. Even if the activation energy is exactly the same, which it is, The fact is we're starting at a higher energy to begin with, so we have to add more energy to the system. Okay, so that's why, in this case, the electronics are allowing us to make the more stable product to follow Zaitsev Rule. Do you see why that in this higher energy conformation, even though we just have to add a lot more to that to get it to go to that, because we're starting in a higher energy state, it's going to take more energy to get there. And even though the actual relative energies here are the same, the net total energy is higher. Okay. All right. Let's see. So when we talk about stereochemistry in our E2 reactions, we're talking about that cis trans isomerization or that EZ isomerization if you have more than 2 groups. Okay. So one way to do it is by the a Fischer projection, but you can also use this projection here. I don't like this as much as the Fischer projection. I think the Fischer projection is beautiful and it's hard to mess up. So, but this is explained in the book fairly well. If you don't get the Fischer projection and you want to do it with this projection, you probably can, but I'll kind of show you how to do it, okay? So when we have these projections, remember all of these are in a straight line, and that these 2 ones at the end are actually pointing down when you first draw the structure, okay? So that means that everything else is pointing up. So we have 2 hydrogens on the same side pointing up, a bromine and a deuterium pointing on the same side pointing up, okay? So in that configuration, your leaving group, which is the bromine, is not opposite anything, right? Because we would have to rotate this around to get it into that anti-position. In fact, we're looking at this deuterium as the one that's going to leave. Okay, so it has to rotate around, giving us this configuration so that we have our bromine opposite our hydrogen, or in this case, deuterium, to give us our trans isomer. And if we rotate it around again and actually remove the hydrogen, that would end up giving our cis isomer here. Okay. So, but you have to remember how to translate this into the fact that all of the groups along this line are up and down to each other, and then everything else is going to be pointing up on each other. So being able to translate that is okay. Okay. And so if you had either configuration right here, notice you're still going to end up with the same alkene. You're going to end up with a cis or trans alkene with predominantly trans alkene as your product. So let's talk about forcing it to go the way we want to go. Okay. So the Zaitsev Rule says that if we have a choice between a hydrogen or a hydrogen, we have a good base, that it's going to make the more substituted product because it's more thermodynamically stable. Okay. But we also said that as we get bigger and bigger, bulkier bases, we have a steric demand that doesn't come in. In fact, that came up in the question we just had right there, is that in that with the cyclohexane, the idea that the methyl group would have a steric demand on it to make it be less favored is possible, but the fact is that it's more thermodynamically stable. But what if your base can't get to your more sterically demanding hydrogen, your more substituted hydrogen? Okay. So that's where we talk about our big bulky bases here. So if we look at this, this is just the base of ethanol. Okay, we don't consider it a bulky base. We consider it a pretty good nucleophile and a very good base. However, this is our classic bulky base right here. This is the T-butoxide right here. And we can even make it bulkier by making it having ethyl groups instead of methyl groups, making it even more. Okay. So, but let's look what it does to the product ratio. When we have a small base, we can remove the protons from here as our major product. If we remove protons from there as our major product, we get the Zaitsev's more substituted product here. Okay, and we still get some of the other ones because statistically we have 6 hydrogens over here. We only have 2 hydrogens over here. So, but we're going to get some, but it's mostly going to be the more stable product. However, as you get to a big bulky base, this methyl group it's being crowded out by the 2 substituents over here, and it's predominantly going to attack these out here, these 6 electrons out here, because there's not as many things around there, and so our product ratio changes. Our product ratio changes where we have the less substituted alkene because of that steric demand. And if we go even really big and even bulkier here, we can even force it to go over even further. Okay, so let's think about this, all right? So let's say you want to make an alkene, but you want to make a terminal alkene, okay? And you have your secondary bromide, and if you ran it in methanol, it would give you the internal alkene and predominantly the trans, okay? But you don't want that. You want the other one. You want the one at the end. So what are you going to do? You're going to change your base to something that will predominantly take off the less less substituted hydrogen and give you the less stable product. And what we call this is, we call this the Hoffman product. He's the guy who came up with the idea that if you use bigger and bigger bases, you can actually form the less stable product preferentially. Okay, so if you want that internal alkene, use a very small base. If you want that external alkene, use a big bulky base like T-butoxide. So that's something to look for when we're looking at our reactions. The thing we're going to do next week is, what's the size of the base? The size of the base is going to determine your product ratio. Okay, does that make sense right there? As you get bigger, you have to go to the less substituted hydrogens, giving you the less stable product, but you can force it to do what you want. All right, so the rule for Hoffman is that you are going to look at the transition state where you can get the hydrogen is going to be anti to your leaving group, but it's going to be one of the hydrogens that is less substituted. So when we were first starting this, we said this is our secondary hydrogen. That secondary hydrogen is going to be preferentially removed because it gives the more stable product. However, the fact that the base can't come in here and give that possible transition state, it has to stick out here and take one of those off there to give the major product being the terminal, in this case, alkene, the less substituted alkene. Okay. So what does that transition state look like? Okay. So let's first look at the transition state that what we thought would happen, where we're trying to remove the hydrogen from that secondary right here. If we look at this transition state where we're trying to remove this hydrogen here, we have this methyl group and these groups over here acting as a steric, acting as big bulky items, so that as our base comes in here, it's being pushed away by this methyl group and this methyl group and this methyl group. Okay. If it's being pushed away, it has to have more energy to get into that position, and therefore it has a higher activation energy. Okay. So, all right, it tried. It didn't have enough energy. It wouldn't remove it from there. So let's try the other one. Let's try the other activation. Let's try to remove the ones that are out here. Now notice when we do that, we still have a hydrogen that's anti to our bromine here, okay? But now there's almost no steric interaction. We have one methyl group over here, and we have 2 hydrogens over here, okay? So that is a lot less steric demand in this, and therefore it has a lower activation energy. But look at the products. In this case, we have a lower activation energy, but we're making the kinetic product because it's a lower activation energy, it's a faster reaction, but it's a less stable product. By just changing our base to make it so we can't overcome this energy barrier here, we're forcing it to give us our, trying to do blue here, because we're not giving it enough energy to come over here, we cannot form our more thermodynamically stable product, and therefore we have our kinetic product in our Hoffman elimination reactions. Okay. And questions on that? Okay, so when we're thinking about making alkenes, we have to think about what is our product? What product do we want? Do we want the more substituted? Do we want the less substituted? That gives us base choice, okay? When we're also thinking about it, we want to look at the idea of if we want to go through an E1 mechanism, we need to think about weak bases in protic solvents because we need to support that carbocation. If we want to go with that E2 reaction, we're using a stronger base, but still in a protic solvent to get us to that. Once we have our E2 mechanism, we want to think, do we want the more thermodynamically stable or the more kinetic product? And that gives us our base choice. More thermodynamically stable, we use a small base. We want a kinetic product, we use the large bulky base. All right, so that's where the Zaitsev rule and the Hoffman rule kind of compete, right? So the Zaitsev rule is telling us we want to remove that secondary or tertiary hydrogen preferentially because it has a lower activation energy, okay? And that transition state gives us our more thermodynamically stable product, okay? Therefore, number one, it has a lower activation energy. It's going to go faster, and it gives us our more thermodynamically stable product. So it's faster and more. It's our kinetic and thermodynamic product. But this energy barrier, usually if you just heat the reaction a little higher, you can get some of that less thermodynamically stable product. Again, this is the kinetic and thermodynamic product. This is a thermodynamic, not as a stable product, but it is a byproduct of the reaction. So switching gears and using a big bulky base, we've changed the dynamics of it by changing the activation energy. Our activation energy, because of sterics, is lower for pulling off our primary hydrogen as opposed to our secondary hydrogen. And when we do that, we form the more kinetic product and the less thermodynamic product. But if we had a lot of energy in there so we could overcome the steric barrier, we would have that higher activation energy, but we'd end up with a more thermodynamic product. So notice it's not 100% either one, because as you're heating the reaction, you're going to have some molecules that will have that slightly higher energy. And that's why you have at least some of the less favored product in both of these reactions. But your major product in the Zaitsev rule is the thermodynamic product. The major product in your Hoffman elimination is your less thermodynamically stable alkene. Okay, do we see why that's why the competition, why they have different energy diagrams? Because their transition states are of different energies based on sterics. Okay, let's see, we got 4 minutes, so let's go. Okay, so let's talk about the Hoffman rule. Okay, so we're basically bulky, poor leaving groups in Regio selectivity. So a bulky leaving group, something that is will come off as a neutral species like water or a quaternary ammonium salt, that is a big leaving group. And so it's going to actually change a little bit of the Regio selectivity, okay? So instead of having something like a halogen, what if we took something like this as a leaving group, okay? You're like, well, you know, an amine, that's a nucleophile, that's a base, right? It's not going to leave as a leaving group, but notice it has a positive charge. So when it does leave and take these electrons, it leaves as a neutral species. If it leaves as a neutral species, that means it's not that bad a leaving group. It's just a large leaving group. Okay. So we can also do that with sulfur here. This is, I forgot the name of it just now. It's dimethyl. Anyway, so sorry. But this also will leave as a neutral species. Okay. Now, what effect does that have on that? Okay. In this case, if we remove our proton from here, that is the least sterically demanded one. This is the more sterically demanded. So having this big group here is still going to allow our big bulky base, Sorry, I'm saying that backwards. No. There we go. All right. So we have our choices between our hydrogens over here, our primary hydrogens over here, and our secondary hydrogens over here. Okay. So if we're using this large leading group here, we actually have a steric demand by the leading group itself, making the more favored, even though we're using a small base, the more favored site is the least substituted site. The leaving group is the big bulky thing in this case, okay? And because the leaving group is so big and bulky, our base is going to come in from that to the least substituted side, giving it as our major product, our Hoffman product. Okay. And again, with this right here, this is the steric demand, so that we can't come in here with a base. It's going to be preferentially coming over here to eliminate that. And it has a lot to do with the energy in the transition state, trying to get everything moving around in the right place. But if we have these large leaving groups that can leave, and they are going to affect the system, large leaving groups lead to Hoffman products. All right, that's 149. I have a few more slides. We'll pick up here tomorrow. I mean, next week. So I'll have a few more slides on here, and then I have a short thing on comparing SN1, E1, SN2, E2, and then we have an activity next Monday. So look forward to that. Okay, I'm going to go ahead and stop recording. If you want to stay behind and ask questions, I have about 10 minutes.